Okay. Somebody must have forgotten this.
Oh, nice. Yours now.
Founders, keepers, right?
Yeah, there's also a fancy little.
Oh, that's sad. Is it? No, no. I'm not taking that. Okay. Let's get going, continue with our chromatography and recap questions. List 3 types of chromatography. Give me one type. Gas chromatography. Thank you, Sophie. Kristen? Liquid chromatography.
Supercritical.
Supercritical. These are 3 types of chromatography. Tyler, Sophie, and Kristen.
Thank you.
Yeah. Okay. So what is the form of the mobile phase in gas chromatography, and what is the form of the stationary phase? Go ahead, Gray.
Yeah,
Uh-huh.
and the stationary phase, can it like depends
Yeah.
like gas liquid, right?
Yeah, so the mobile phase always gas, and the stationary phase can be liquid or solid. Yeah. Okay.
So,
Solid.
okay, sorry.
So- solid. Yeah. No, no. Okay. Same question for partition chromatography. Graham?
Liquid.
Liquid and liquid. Thank you. Adsorption? Adsorb on something. Liquid and solid. Thank you. Yes. What is a partition coefficient? Tyler?
It's like the rate at which the mobile phase leaves the stationary phase.
Partition. The rate,
No.
that would be the rate of the mobile phase. There is something called the rate of the mobile phase. Oh, yeah, that would be correct if I'm asking about the rate. Yeah.
It's the ratio
Yes.
of the concentration of your solute, your thing you're looking at in the mobile phase versus this.
Yes. So partition, your solute is partitioning. So always remember this partition, it's partitioning, distributing itself, but since it's liquid to liquid, we call it partitioning. So it's the constant at equilibrium. It is the concentration in the mobile phase of the solute relative to the concentration in the stationary phase. It's very important that this should be at equilibrium. When we reach equilibrium, we get a partition coefficient that is constant. Okay, so in reverse phase paper chromatography, what type of compound travels the most with the mobile phase? In order to answer this question, in reverse phase paper chromatography, which phase is polar? Do you remember? Is it the mobile phase that is polar or the stationary phase is polar?
Mobile phase.
The mobile phase is polar. So what travels the most in the mobile phase? A polar constituent or a non-polar?
Polar.
Thank you, Razi. Yes, it is polar. So it dislikes the stationary phase and travels faster or more with your polar mobile phase. Thank you. All right, thin layer chromatography. I have a story to tell you about TLC. What does TLC stand for other than thin layer chromatography? Okay, I want to hear it from Graham.
Tender love and care.
Yes. Let me tell you, the first year I was teaching phenanyl, my daughter was 5 years old and she was in kindergarten all day. So I went to pick her up and I saw her sitting in the teacher's lap on the teacher's. So I said, okay, so what happened? And she goes, your daughter needed TLC today. And I was like, and then I was introduced to tender love and care that for the first time. I didn't know of TLC at the time. So my mind was in chromatography. Okay, so it has similar principle as paper chromatography. And it was developed to replace paper chromatography because it has better resolution. Who can define resolution? What does resolution mean? Kendall, show up better. So you're on the right track. If you have two constituents, when I say I have good resolution, what does that mean, Kristen?
That you're able to define between the two.
You're very, yes. What were you going to say?
I was gonna say it, defined and it's more clear. That was
Clear separation. Okay, so you can clearly resolute, separate. Okay, it's kind of like reaching a resolution. So reaching a solution in chromatography, that means separate, well separated. Okay, so it has better resolution. So two compounds using paper versus thin layer chromatography. With thin layer chromatography, I get better separation, better resolution. Why? Because we have smaller uniform particle size. So think about your paper with crude cellulose. You don't have really homogeneous particle size. Whereas with thin layer chromatography, usually you have aluminum foil, aluminum background or glass. When I was a student, it was a glass and inert. And then you have a layer of silica mostly. A very thin layer, finely defined particles that is on that surface, the inner surface. So uniform small particle size. With that, we have better separation when you have uniform particle size and small. We'll talk about resolution more in a couple of lectures, but that's why thin layer chromatography has better resolution because particle size is consistent and uniform and small. Because of that, we have faster separation and better reproducibility, meaning every time we run, we get similar results or similar separation. So like I said, you have an inert support. Mostly, it used to be in the past glass. Now you can actually buy aluminum foils, thin layer chromatography. You can buy them. And we use them in the labs. If you are taking experimental nutrition, you're probably going to use that, the aluminum foil one. So it is an inert support. That means it does not interact with your sample. And it has this thin layer of sorbent. And most common, it's silica. You can have alumina or cellulose, but mostly common one is silica. We can use it as normal phase where we impregnate the silica with water. So normal phase, then the stationary phase is your polar water. Or you can use it in reverse phase, impregnate it with a non-polar liquid, which could be hexane. Or you can derivatize the functional group into a charged group, and you can use it as ion exchange. And this process is for screening. It's done mostly for screening. And once you separate, you need to visualize or see the separated components. If it's amino acid, you spray with anhydrous, or you can spray with a very strong acid like sulfuric acid. You burn the organic matter, or you can spray with a fluorescent. And then you can look at qualitatively, look at the separation. Here's an example of phospholipid, monoacylglycerol, diacylglycerol, a free fatty acid, triacylglycerol, and then your sample. So these are standards, and then your sample. Then you can see what's in the sample of fat distribution. You can quantitate, so you can measure the density of each of these spots and relate that to concentration. So you would have to run a standard curve in order to do so, or you can take that spot, you scrap it off, elute it with chromatography and quantify it. Okay, any question? So I want to switch gears to column chromatography, which is the most commonly used type of chromatography. So there's the column GC and then there's the column LC. In this image, in figure 12.2 in your chapter 12, this shows low pressure chromatography. So you have something called low pressure chromatography, and you have high pressure chromatography, or we call it now high performance liquid chromatography, HPLC. So we'll talk about both and how they are different. And in liquid chromatography columns, so you have different columns, literally columns, and they come in different sizes. For low pressure chromatography, you pack your column. You can buy packed column, but usually you pack your own column with stationary phase. They come with different lengths and different widths. So you have all sorts of sizes, basically, and then you can pack them with different material. Based on the material that you use, you will have size exclusion chromatography or hydrophobic interaction chromatography or whatever type of or method of separation, mode of separation. So the way you pack them usually have instructions by the manufacturer of the stationary phase that you would usually prepare it in a slurry, and you pack your column under specific pressure and using a pump to pump in your stationary phase. Okay, so what you see there is your column that you packed, and then you have peristaltic pump, and usually you have at least one solvent, but you can have two solvents that you mix to generate your mobile phase, right? You can actually change the concentration of the mobile phase over time as well. But hold that thought. And then you inject, there will be an injection port where you inject the sample onto the column, and your pump is pumping the mobile phase, and your mobile phase starts carrying the sample down the column, and your constituents or solutes start interacting with the stationary phase. And based on their variation in how they interact, they will start separating. And they will start separating and go down to the end of the column and get directed to a detector. Well, since I have this, I can point. Very nice. So they go here onto a detector. It could be a UV detector, refractive index detector, a fluorescence detector. We're going to talk about all those detectors later on. And then you get a readout, a chromatogram. And then after the detector, they can go into a waste, or you can collect the peak or the whatever it is, protein. I'm used to collecting protein, carbohydrate, whatever you're separating, you can collect it and use it for different tests. You can also have a reaction. If we're isolating, let's say, enzymes, and we want to determine the activity of the enzyme, we can, or a substrate to the enzyme, we can take it into a reaction chamber, have it reacted, and then you can measure enzyme activity or substrate concentration. So It's a very cool process. It's mostly used to get a fraction in a sizable amount. If you're only looking to detect and quantitate, we often use high performance liquid chromatography, where the columns are pre-packed for you under pressure. Even those come with different sizes. When we talk about resolution, we're going to explain that the longer the column and the narrower it is, the better is the resolution. So remember this for now, and we're going to talk about it more when we cover resolution. Longer columns, narrower in diameter, will have better separation, usually, so better resolution. So your stationary phase is packed in the column, and then your mobile phase is going through the column and carrying the constituents of your sample, and they're separating based on their affinity to the stationary phase, how much they like interacting with the stationary phase. If neither of them are interacting, they're going to just go through together and reach the detector. Defies the purpose of chromatography. We select stationary phase based on what we know about our constituents to make sure that they separate. Okay? So our first goal in chromatography is, let's see who was paying attention. I can see you so tired. Still Wednesday, you still have 2 more days to go in the week. Almost Friday. Separate, yes. So our goal is to separate. That's the first thing. So we want to ensure that we use the stationary phase that will allow the constituents to separate. Second goal, what could be our second goal? After we separate, detect. Very good. After detection, what do we want to do? You detected something. So, Millie? So we separated, we detected using a detector. And then after we detected, what do we want to do? Before quantification, that comes next. Before you quantify, we can collect, but we want to identify. We want to know what it is. So we want to detect something, then we want to know what it is. And then if we have standards, we can quantify. All right, so repeat with me. Separate, detect, identify, quantify. You can go home. No, sit down. Okay. All right. So let's talk about isocratic versus gradient mobile phase. This is very, very essential in liquid chromatography. So isocratic mobile phase means that your mobile phase constitution or concentration or type does not change throughout the run. Running water, we're running water throughout. Running buffer throughout. Hexane, acetonitrile, 100%, isocratic. We're not changing anything about our mobile phase. We're not even changing the rate, between how many milliliters we're pumping per minute. We're not changing the temperature. We're not changing anything. Isocratic. Gradient. What do you know about gradient? Or have you heard that term? So what does it mean, Graham? You remember? Okay, so we changed the concentration or the composition of our mobile phase over time. So we will have a time program where we change the characteristics of it.
Would it also include changing the temperature of the column over
Yeah,
time?
changing temperature, because that would change viscosity and how fast we reach equilibrium. And changing, so changing temperature, changing the rate. But mostly when we talk about gradient mobile phase, we are talking mostly about changing the constituents of the solvents that we're using. And this is often happens when we know that interaction is happening and very strong, and we want to make sure that we get the analysis done in a shorter period of time. So your constituents will eventually leave the column, but it might take hours. So gradient elution often is done to kind of speed up your separation and elution. So you make, so there's another term that you're going to hear or learn, make the mobile phase stronger. Or in other words, you're going to hear me say, increase the strength of your mobile phase. If you remember the example about the little girl and justice, you increase the strength of the mobile phase by buying her something to come out of that store. So that mobile phase now has a toy or a very pink t-shirt or PJ, and then she's gonna come out faster. Chromatography, same way. If you can increase polarity or increase the organic solvent or increase salt or increase pH, decrease pH. Anything you do to the mobile phase, we call it enhancing the strength of the mobile phase or increasing the strength of the mobile phase. No matter what it is, you're just making the mobile phase stronger to attract the compounds that were interacting with the column. Questions? Yes.
So, first of all, from what I remember, it's really hard to just stop the column. Is there a way to switch the mobile phase to freeze the things separated? Because what I'm thinking is if we're going to speed up the removal, then you potentially mix them back together.
Mix them back together?
If you're speeding up the mobile phase, increasing the strength of the mobile phase, pulling them through faster.
Yes, but you don't want, okay, so the only time you don't freeze, you kind of go from gradient to isocratic. And okay, so you asked sooner that I was going to go into that when I talk about resolution. But let's say you have you don't have perfect separation, okay? And you're going with gradient elution. And you really don't have perfect separation. It didn't go all the way down to the baseline. And let's say this is minute 5, this is minute 7. That's time, okay? And this is your signal of the detector, okay? So, and you're going gradient. What can you do to enhance separation? Here, between 5 and 7 minutes. Between 0 to 5, you're going gradient. Anybody did a chromatography before?
You just keep the gradient stable.
You go to isoprep. So you can change that later on. You can program so that you go gradient, so you kind of enhance the movement. And then if you probably have multiple in there, everything is separating. These two are not. So at the time between 5 and 7 minutes, you do isocratic and then you go back to gradient. So you improve separation and then you still enhance how quick your analysis is. And that was something I was going to cover in resolution, but since you asked, I'll give you a sneak peek. Other questions? Okay. All right. I'll briefly introduce supercritical fluid chromatography. It's just one slide. We're going to continue focusing on liquid chromatography, but just that you know what it is. Here you use a mobile phase that is originally under ambient conditions a gas. And the common one is CO2. You increase temperature and pressure, you liquefy CO2. Sometimes you add methanol if you want to enhance the movement of slightly polar compounds. You add methanol because it's a polar organic solvent. CO2 liquid, very non-polar solvent. This is used mostly to separate non-polar molecules that are not volatile. So usually with GC, non-polar molecules that are volatile, you can separate them by GC. Supercritical is you have non-polar molecule, they are non-volatile, and they are thermally labile, meaning not stable. They can degrade with temperature. So we cannot use GC. So we use this supercritical fluid chromatography. And this liquid CO2 had high diffusivity, meaning it's really not dense, has low viscosity, and it allows movement to happen very fast. Because of its low viscosity, it moves smoother and results in better resolution and less analysis time. Okay, so with that, the stationary phase is similar to what we use in high performance liquid chromatography, but detection or the detectors are similar to those used by GC. So later lectures, we're going to talk about stationary phases in HPLC, and Gary's going to talk about all possible detectors for GC. So this is all that I want you to know about supercritical fluid chromatography. All right, now I'm gonna, yes, yes, it is used. In the food science building, no. We don't have it. We don't have a supercritical CO2 generation.
Can you give an example of what it?
Yeah, so let's say fatty acids, direct analysis of fatty acids without derivatization. They are non-polar and they're thermally labile. Yep, absolutely. Okay. Physicochemical principle of chromatography separation, or in other words, mode of separation. So sometimes I ask you, what's the mode of separation? You want to say, okay, adsorptive chromatography, ion exchange, or partition chromatography, normal phase. So what is the physicochemical principle behind the separation? So we're going to spend time talking about all these different types of separation. The first one is adsorption, and there are multiple forms of adsorption chromatography. You have simple interaction by polarity, or you have interaction by charge, ionic interactions, or you have interaction by affinity, very, very specific, like lock and key, very specific form of interaction. And then you have the partition chromatography. We talked about partitioning between two liquids, mostly based on their solubility or polarity. And then we have size exclusion, no interaction. It's just based on the size of the molecule. So it's kind of like gel filtration. You hear it called multiple names, molecular exclusion, excluding based on molecular size. And then you hear it say size exclusion chromatography. So molecular exclusion, size exclusion, gel permeation or filtration all mean the same thing. So it just have multiple names in literature to confuse you, but it means the same thing. So we're going to talk about all of those, but this is a summary figure 12.3 in your chapter. And very expensive figure, by the way. had to pay a lot to include it in the chapter. But it's very good illustration. Okay. Any questions so far? All right, so we'll start with adsorption chromatography, where you have solid stationary phase, and it should say liquid solid. Sorry. I'm gonna have to, I want to correct it. All right, bear with me. You can breathe. All right. So it is liquid chromatography. So it is liquid mobile phase and solid stationary phase. Okay, very slow. Come on. So your stationary phase is the adsorbent. Finely divided solid, so a small particle size. The smaller and the more uniform, the better the resolution. And it allows differential interaction. So the interaction with different components are very specific. And the interactions are via non-covalent interaction. So we need interaction. If we don't have interaction, we won't get separation. And the interactions are non-covalent. If you have covalent interaction, we can take it out. It's irreversible, or we have to use strong measures to break covalent interactions. We don't do that. Now, what is shown here is a demonstration that with adsorption chromatography, there's always a limit of how much sample you can put on the column. So unlike partition chromatography, it is concentration dependent. So the adsorption coefficient is not a constant. It is dependent on the concentration of the solutes we put on the column. So every time we use adsorption chromatography, depending on the column, each column or each stationary phase comes with a maximum load. You need to know the maximum load. How much is the maximum we can put on the column? Otherwise, what this is illustrating here, so what is illustrating, these are the functional groups. So those red triangles are functional groups on your stationary phase. Those are your constituents. The blue are your constituents. If I overload, put more than the capacity of my stationary phase, you're going to have few that do not interact. So what happens is, this is what's going to happen. You are running your chromatogram, and then as you're going to see a peak coming out as soon as we call it with, what do we call that first? I'm losing my jargon.
Front? No.
Solvent front, yes. Thank you. Solvent front. Your solvent front usually is a small peak. And it's just when you run your analysis, when the solvent reaches the detector from the time of injection, the detector gives you a blip. Oh, something hit. So it's nothing, it's just, we call it the solvent or void volume soon. We will talk about void volume. Solvent front or your void volume. So basically the mobile phase going through the column without interaction, without any delay. Okay, so you will see a peak here that's big, and then you will see another peak of the same compound because you injected too much. Some of it did not have a chance to interact, left the column right away. some interactive comes out. So you have something called split. P. Incorrect. Wrong. You don't want that to happen. So that's why it's very important that in adsorption chromatography to basically make sure you know what the load is or maximum load or concentration you can have on the column. Okay. Yes.
Is that labeled as like moles per liter or?
Yeah, it will give you a concentration that, yeah, whatever concentration, molarity in percentage, in sometimes it is in parts per million, depending on the size of the cup. Again, this needs to be swapped. I'll do that later. So stationary phase can be silica, alumina, or charcoal, for example. And here the elution is depending on relative polarity. So these are all, so the first two are polar, charcoal is non-polar. So if we have polar, then this would be normal, kind of like normal phase. Our separation is based on polarity, and the most polar will interact the most with the column, and the least polar will leave first. Charcoal is the opposite, reverse phase. So solutes and solvent, the mobile phase, compete for active sites on the stationary phase. And then you change the strength of the mobile phase will alter how the solute interact with the stationary phase. So let's say you have silica and then you are using an organic solvent like hexane. And now all of your polar compounds are interacting with silica and you're using hexane. You want them to come out, you make the solvent less polar. Or if you're using acetonitrile, is also non-polar, you can increase the water concentration. And then you will make it more polar. That allows separation. Most common stationary phases, you have something called C8 or C18 or C40. What does that mean? C8 means 8 carbons. So you would have a chain of carbons attached to the silica functional group. Or you have 18 carbons, or you have 40 carbons. The longer the carbon, the more hydrophobic you're making your stationary phase. For example, C18, you're going to use it for separation of caffeine. If I want to separate carotenoids, for example, they're a little bit less polar, so I can use C40. Longer chain of carbon, I make it less polar, and then my carotenoids will interact better with the column. Again, I always try to seek interactions with the column. Questions? Partition chromatography. So the solutes, we talked about it already. Partition between two liquids. Also, the elution of solutes depends on changing the nature of the phases, combining solvents, changing pH, adding salt. When the most polar phase is held stationary, it's normal. We said this before. When it is the least polar is held stationary, it will be reverse phase. But there is also a hydrophilic interaction chromatography and a hydrophobic interaction chromatography, which were very, very specific. And then we'll tell you the difference between normal phase and hydrophilic interaction chromatography, and then reverse phase and hydrophobic interaction chromatography. There are 4 different things, okay? We'll talk about them individually. So you have coated support. So sometimes you have the silica gel and then you have hydrated silica or impregnated with water. Then this is your normal phase chromatography. Sometimes you have bonded. So either coated, impregnated just with water, wetted, for example, or bonded. So the liquid phase is covalently bonded to a support via chemical reaction. So C8, C18, or C40, they are bonded phases, chemically bonded phases. So silica is bonded to C8 or bonded to C18 or bonded to C40. Okay. You tired or not yet? Okay, I'll let you go 5 minutes early because I need to spend time explaining this and I don't want to start it and stop it. All right, so breathe, go outside, enjoy the sun, and then I'll see you on Friday.